Well, what is quite a complicated business is this. You've got an image in the eye, which is perfectly straightforward, dead simple optics. It's simply that a point out there in external space is registered on a little region of the negative in the camera or the image in the eye. So if you've got a point out there, it goes through the eye and then it gets to a given bit of the retina. So you get a pattern on the retina or a camera corresponding to where objects or parts of objects are in the external world. That's easy. But of course, objects are at different distances. So what the brain has to do, and when you're looking at a photograph, is to judge where the objects are, and when they get further away or are further away, they get smaller by optics. But that might be that they're further away or they're actually smaller. So there's always a judgment that needs to be made. Now, there's a process in perception itself which to some degree compensates for the shrinking of the images with distance. And this is called size scaling. And I'll pick up an object if I may. Let's start with it. This is actually rectangular. This is at right angles to you. Now, if I move this further away or nearer, it changes size in the camera and in your eye. Is that enough to see the difference? Yeah. Should be, yeah. Now, you can either see that as this thing shrinking and expanding, which it might be, or as not actually changing its size, but changing its distance. And here probabilities come in. If it's unlikely to be changing its size, if it's a table mat or the head of your friend, much more likely that you're changing distance, and that's what you see. But you can play party games on this. Imagine that you've got a balloon, and let's say, to make it extreme, you have it luminous in the dark. You then make it get bigger or smaller, blow it up or let it down. You see it as getting bigger or smaller when actually it's changing size. Or take a cartoon film. You represent something getting further away or nearer by changing size on the screen in the cinema. And you normally see it as going in and out in depth because, and simply because, it's jolly unlikely that it's changing size. People's heads don't change size. Even table mats don't change size. Now, it happens that balloons can change size. They're unusual objects. So what happens is that the brain makes a decision unconsciously about whether it's changing size or whether it's changing distance, and the probability is set to what happens pretty well. But in addition to that, or related perhaps to that, you've also got compensation going on. That when you've got a change of signal distance or size, the brain can compensate. This is called a Ponzo illusion. If we look at a photograph of a scene in perspective, like railway lines, the two white rectangles stuck on the photograph are actually the same size. But the upper one, similarly to the original Ponzo figure, will look a bit bigger. Now, you see here that it's really further away by perspective. Size constancy operates, which expands further objects as they shrunk in the eye, and that compensates for this optical shrinking. So what we're seeing here is what is usually a useful correction for the shrinking of pictures in the eye. Here on a flat picture, it produces a distortion. The compensation is not appropriate to a picture plane, to a flat plane, though it is to the real world. And so what is normally useful helps you to see things correctly. Here produces a distortion as it's a picture.